Everyone, I'm Taeyoon Kim from Hanyang University, and I will be presenting our work on HybridServe, an adaptive runtime selection system that combines WebAssembly and containers for edge servers computing. This is joint work with Seokhyung-gang, Woo-Yeon-song from Kookmin University, and I contributed equally to this research. First, our work is motivated by the growing demand for edge servers computing. Today's IoT environments consist of over 25 billion devices generating exabyte scale data. Sending all this data to the cloud introduces latencies of tens to hundreds of milliseconds, which is unacceptable for latency critical applications like autonomous vehicles. Edge computing addresses this by processing data closer to where it's generated. Serverless is particularly well suited for edge environment. The on-demand execution and scale-to-gel model efficiently utilize limit edge resources. Additionally, IoT devices generate events intermediately, which aligns naturally with the event-driven serverless paradigm. However, current serverless platforms face fundamental challenges. Most platforms rely on containers, which offers major tooling and proven reliability. But containers suffers from cold start latencies, lagging from hundreds of milliseconds to several seconds. A significant bottleneck for responsive edge applications. WebAssembly runtimes such as WASM-Time, WASMer, and WASM-Edge can achieve cold starts under tens of milliseconds. However, WebAssembly exhibits slower execution performance due to runtime completion and system code translation overhead. Creates a fundamental trade-off. Containers are slow to start but fast to execute, where WebAssembly is fast to start but slower to execute. This trade-off becomes particularly problematic at the edge. Edge system must handle both latency-sensitive IoT events where fast startup is critical and compute-intensive tasks where execution speeds matter more. These conflicting requirements cannot be optimally addressed by a single runtime architecture. Observation motivated our development of HybridServe. This trade-off becomes particularly problematic at the edge. Edge system must handle both latency-sensitive IoT events where fast startup is critical and compute-intensive tasks where execution speed matters more. These completing requirements cannot be optimally addressed by a single runtime architecture. The hybrid server design is shown in this diagram. When a request arrives, the system checks for an available worm container. If a worm container exists, the request is routed to the container for high-performance execution. If not, the request is routed to WebAssembly for immediate response, where a container is prepared in the background for subsequent request. This adaptive mechanism ensures fast response regardless of system state, either the WebAssembly instant startup or containers fast execution. In section 2, we examine lightweight runtimes for edge serverless. Where most serverless platforms rely on containers, they present three key limitations for edge development. First, cold start latency of hundreds of milliseconds to second is too slow for real-time responsive. Second, container images are 70 to 80 times larger than WebAssembly modules, which is problematic for storage-constrained edge devices. Third, containers are architecture-specific, requiring separate images for x86 and ARM platforms. In short, containers do not meet edge requirements for fast initialization, small footprint, and architecture independence. Also, we evaluate several alternatives. Lightweight containers using Erfan Linux reduce image size by retain OS level isolation overhead. Unicorners require application recompilation, limiting practical adoption. WebAssembly provides sandbox execution, fast initialization, and architecture independence. The trade-off is slower execution performance. However, given the critical importance of fast startup and portability at the edge, we focused our analysis on WebAssembly as the most promising alternative. Section 3 covers WebAssembly runtime compositions. WebAssembly's key advantages are architecture independence and the ability to compile code from C or C++ and Rust into a unified bytecode format. WebAssembly binaries are compact, typically tens of kilobytes to a few megabytes. With low initialization overhead, these properties make WebAssembly well suited for resource constraint and HD environments. WebAssembly runtimes support three execution modes: interpreter mode, JIT mode, AOT mode. Uh, Interpreter mode executes bytecode line by line with minimal startup overhead, but very low execution performance. JIT compilation converts bytecode to machine code during execution, enabling runtime optimization and caching, but higher initialization overhead. AOT precompiles bytecode before development, providing both fast startup and consistent execution performance. Makes AOT ideal for serverless workloads where fast code start is critical. As shown in Table 1, we evaluate three major WebAssembly runtimes. Wasm time use crane lift. Wasmer supports crane lift, LLVM, and single pass backends. And Wasm Edge use an LLVM-based compiler. All three supports both JIT and AOT modes. The choice of compiler's backend significantly impacts performance characteristics, which we explore in our analysis. WebAssembly executes in a sandbox by default, preventing direct access to system resources. The WebAssembly system interface, aka WASI, addresses this limitation by providing a standardization API for controlled access to host OS capabilities. As shown in this diagram, the runtime intercept WASI calls and translates them to corresponding system call. This translation does introduce overhead, which is one factor in WebAssembly's slower execution compared to native code. Section 4, presenting our runtime analysis. We designed the experiments to reflect edge constraint, limited resources, intermediately traffic patterns, a strict latency requirement, and heterogeneous hardware. We evaluated three WebAssembly runtime and standard Docker stack with constraint and runtime. Experiments were conducted on our Intel NUC and NVIDIA Jetson Orinator. Figure 2a shows execution time across multiple iterations. The Wasm at JIT research show as blue pentagons. remain consistently high at around 15 seconds because WASM-H JIT does not implement compilation caching, resulting in recompilation overhead on every invocations. More broadly, JIT is fundamentally unsuited for serverless workload. The scale to zero characteristic cause runtime unloads during idle periods, invalidating any cache. This makes JIT less effective for edge workloads. Figure 2b compares JIT and AOT in WASM time. The dashed lines represent AOT execution, showing constrained fast cold start after compilation. The trade-off is that AOT binaries are hardware-specific. However, for edge developments with non-target hardware, this is generally acceptable. Figure 3a and 3b characterize compiler performance. Figure 3a shows the expected trade-off between completion time and execution performance. Figure 3b shows microarchitecture differences. CraneLift achieves the highest IPC, indicating efficient instruction level parallelism. LLVM shows 3.1 times fewer L3 cache miss than single path, demonstrating superior memory optimization. Figure 3C and 3D compares runtimes using identical compiler backends to isolate implementation efforts. In Figure 3C, both WASM time and WASMer use CraneLift, yet WASM time achieves 17.5% faster execution with fewer system calls. Figure 3D compares WASM-H and WASMer with LLVM. For image processing, WASM-H is 16.5% faster, but for Jinja template rendering, WASMer is 28.9% faster. This suggests that different runtimes are optimized for different execution patterns. Table 2 presents our direct comparison of WebAssembly and containers. For cold start, WASM is 87.68% faster. For power consumption, WASM use approximately 9.3 more energy. These results clearly demonstrate the complementary characteristics of the two techniques. To summarize our analysis, containers provide fast execution and power efficiency, but suffer from slow cold start and large images. So we using Jasnori Nano devices to evaluate this. WASM provides fast cold start and small images, but with slow execution and higher power consumption. Neither technology universe superior. They have complementary strengths. This is finding motivates our hybrid approach. Rather than choosing one runtime, we can straight right to use both. Section 5 presenting HybridServe evaluation result. Evaluations, as I mentioned, evaluation was conducted on a Jasnori Nano using traffic patterns divided from the Azure function dataset. We tested our HybridServe for pattern, steady, fluctuating, spike, and jump, representing realistic edge workloads. Baseline were WASM only using WASM time, CraneLift with AOT compilation, and container only using the standard Docker stacks. This is evaluation result. Figure 4a shows cold start overhead. The container only approach incurs 8.7% to 14.5 higher cold start latency than HybridServe across all traffic patterns. HybridServe avoids container cold start penalties by routing to WebAssembly when no warm container is available. Figure 4b shows response time. HybridServe achieves an average of 43.34 milliseconds compared to WebAssembly only. A 78.5 improvement. When warm containers are available, Hybrid allows to them for native execution performance. In conclusion, our analysis demonstrates to WebAssembly and containers have complementary characteristics. WebAssembly achieves 88.1% cold start reduction and 99.17% smaller images, but with 36 slower execution. HybridServe exploited these complementary strengths through adaptive runtime selection, achieving 43.11% response time reduction compared to WebAssembly only, and 91.9 cold start reduction compared to container only. For future work, we plan to extend HybridServe to distributed edge cloud cluster, designing an intelligent scheduler that considers cluster-wide resource conditions for dynamic routing optimization. Thank you for your attention.
Thank you. Do we have any questions?
Yeah, there's question.
Yeah.
Thank you for the talk. That's very interesting. Which compilation of WebAssembly did you use for your experiments?
We repeated our one experiment environment. The idle experiment environments is like Knative or something else, but at the time we just built our one experiment environment.
But did you use WebAssembly? Did you have like the interpreted mode or
Yeah.
just in time execution ahead of time?
Yeah.
Did you observe some of this compilation? So any difference in that?
Oh yeah, we just compared the execution mode and compiler mode. I think there is no strict answer, but depending on workload or depending on some code and network latency, there's many factors to to calculate this. I'm not sure about that. Yeah.
So thank you for the presentation.
Yeah.
So what kind of applications you are targeting in IoT? We have wide range of applications.
Yeah. We use full workload, like plot operation is compute optimized. Jinja workload is for web page template, and Limpag and Mem are like compute intensive workload for evaluate this.
I think there's no more question here. Oh, there is? Okay.
Thank you for the presentation.
Yeah.
And I think I got your meaning that when the request receives,
Yeah.
yes, if there is a warm container available, it is directed to the container.
Yeah.
And if not, it is directed to WoSM and starts a warm container at the meantime. So how will the request be like in the real world scenarios in your settings?
Real world worker.
What?
What?
So how will the
yeah.
request be like
Yeah.
in real scenarios?
Actually, we didn't test real-world workloads, but I think there are some database query or something else.
Okay,
Yeah.
so one container means that if the
Right.
container, if there is a container has been started, then
Yeah.
we direct it to it. And if there is no container available, we direct it to WASM and
Yeah.
the starter container to
Yeah.
warm it up.
Yeah.
Okay, thank you, thank you.
Yeah.
Any other questions here? Okay, there's no more questions here, Alec. Oh yeah,
Sorry,
Andy, sorry.
What potentially is is there any overhead of your solution? Because now you need to maintain both infrastructures.
Yeah.
Right? So
Yeah.
did you do any calculations on that?
I think that this work is focused on cost effective, server is always suffers from cold start, but I think this hybrid serve potentially solve that problem. Yeah.
Okay. Yeah, so maybe Alec, you can check if there's questions online.
I do not see any questions online. I'm also checking Discord, so I think we will proceed with the next. So I checked with the next speaker. He's stuck at the airport. He sent me a message. He may be trying to get, he has actually two talks. He has also the talk at the end of the workshop. But very unlikely he will try to maybe find if he can get connection from the airport, but it did not happen. So I'm going to play the talk right now.
Okay, so we're done with the first speaker, right?
I think so, unless there are any pending questions.
Okay, then thank you.
Yeah, thank you for the first presentation. Okay, I will share my screen. Let me know if you cannot hear or see what I'm going to play back this video.
Good afternoon, everyone. My name is Erfan Darzi.
It's good.
Thank you.
It's good.
And I'm presenting my work that has been done together with my collaborators. And the title is Elastic Reconfiguration with PCIe-Aware placement for multi-tenant GPUs. Let me start with setting the context. Serverless and elastic cloud platforms are increasingly popular and are increasingly supporting GPU-accelerated LLM inference for applications like interactive chatbots, agentic applications, and real-time recommendation systems. These platforms promise dynamic scaling and pay-as-you-go pricing, which is great for the users. However, there is a fundamental challenge delivering predictable performance under multi-tenancy. In shared GPU environments, we face what we call noisy neighbor interference when co-located tenants like batch training jobs, data loaders, or I/O-intensive background tasks create significant tail latency jitter. This violates service-level objectives and degrades user experience. For serverless LLM inference workloads, unpredictable time to first token latency directly impacts responsiveness, especially critical for streaming generation or multi-step agentic workloads. A key source of this interference is contention for shared PCI bandwidth. This becomes a bottleneck during intensive data transfers between host and GPU. The challenge is particularly acute in cloud environments where users operate within virtual machines with limited visibility into hardware topology, including PCI lane allocation and NUMA domains. Existing GPU isolation mechanisms have limitations. Multi-instance GPUs or MIG provides hard isolation for compute and memory, but it's not designed to fix any problem that might arise for shared PCI path. Multi-process services or MPS improves sharing efficiency, but offers weaker isolation. So we need something better. Our work addresses these challenges with 3 key contributions. First, we present an elastic resource allocation controller that dynamically adjusts GPU isolation through MIG reconfiguration and PCIe-Aware placement. Second, we demonstrate SLO-compliant LLM serving on a 16 GPU cloud cluster using only VM-level controls, which means that we have no special privileges for this work, and we achieve a 32% reduction in SLO violations. And third, the part is we evaluate our system on VLLM serving, Olmo 2, 7 billion instruct, showing a 10 to 15% improvement in time to first token, P99, demonstrating practical applicability to production workloads. So let me walk you through our system architecture. Our controller has 3 main domains. First, the monitoring domain continuously collects performance signals per tenant tail latency, including TTFT and VML metrics for GPU utilization, PCI encounters, and host I/O statistics. It detects SLO violations and performs root cause analysis. Second, the decision engine, implemented as a finite state machine, selects from 3 intervention strategies based on the diagnosed issue. We'll dive into this in a moment. And third is the execution path, which applies changes with standard tools like NVIDIA SMI for reconfiguration and process pinning with CUDA visible devices and C groups for resource limits. Importantly, everything operates with a feedback loop back to the latency tracking to validate that our interventions are actually helpful. So our controller operates within a well-defined and 3-tier decision space. The tier 1 is lightweight guardrails. These are quick, low overhead interventions like adjusting MPS quotas to cap tenant concurrency or applying cgroup I/O throttles to limit disk bandwidth of noisy neighbor background jobs. And you can think of these as turning down the volume on noisy neighbors. And tier 2 is PCIe-Aware placement. This is another form of intervention, which happens where guardrails aren't enough, and we migrate tenants between MIG instances, and we query GPU and PCI topology using DCGM and NVML to form a placement score for each candidate MIG instance. The score penalizes sharing a PCI root complex with bandwidth-heavy tenants so that we can co-locate them with high I/O NUMA domains and proximity to IRQ-heavy CPU cores. So we can avoid getting to proximity of these busy MIG slices. And the third intervention is to reconfigure the MIG dynamically. And this is our strongest intervention. We changed the size of a tenant's MIG profile, basically. For example, we upgraded from 1 gigabyte and 10 gigabyte to 2 and 20 gigabytes on a 100 GPU. This provides a stronger hardware isolation for compute and memory resources. And our policy is designed to be simple and robust, and it gets triggered when a tenant's P99 latency exceeds a threshold for certain consecutive observation windows. And we use 3 windows to avoid reacting to transient spikes. And after the trigger happens, we first diagnose, we try to understand the root cause, and we use secondary signals. So whether it's high PCI or is I/O pressure. So then in that case, we need to apply guardrails. And for example, if we can diagnose the root cause to be a compute or memory contention, we upgrade isolation through placement. Or if we want to be more interventional, we do make reconfiguration. And conversely, when the performance has been stable and when it's within the SLO for a sustained period, we relax the isolation to free up the resources and improve cluster utilization. So critically, to prevent oscillation, we enforce minimum dwell times between actions and cooldown periods after moves, so that we can avoid a lot of interventions or more frequent actions in case the tenant is stable. This ensures that we can have a stable operation and it's suitable for production environments. For our evaluation, we use a 2-node cluster with 2 AWS instances. That's 16 NVIDIA 800 GPUs total, and are linked with 200 GB per second InfiniBand. We designed the 3 co-located tenants. T1 is our latency-sensitive inference workload with a 15 millisecond P99 SLO. This is our primary tenant we are trying to protect. And we have other tenants that are actually there and designed to be interfering in different ways that are the main concern of this work. T2 is the second tenant, which is a bandwidth-heavy ETL process that continuously moves data between the storage, and also it moves the data between the storage and GPU to create PCI contention. And T3 is a compute-heavy training job that maxes out SM occupancy. And we toggle T2 and T3 activity dynamically that we can create realistic interference patterns that happen in real production environment in multi-tenant GPUs. And we repeat all the experiments 7 times with fixed seeds so that we can have a more statistically significant and confident results, and our results are reported within 95% confidence intervals. So let's look at our results. This table shows our ablation study, where we systematically evaluate each component, starting with the static MIG as our baseline. So it's 16.4% SLO miss rate and 20 millisecond P99 latency. And with guardrails only, we see modest improvement. It's 14% miss rate and 19 milliseconds P99. And you can see the results for PCIe-Aware placement alone, which is 13%. It is a more substantial improvement. And if you do dynamic MIG reconfiguration alone, it's the strongest single component action. And if we combine all these elements together, so our full system that combines all the 3 interventions, we have 32% reduction in SLO violations if we compare to the baseline. So importantly, we know that the throughput cost is minimal. So that's where the trade-offs come to play. We only have 3% degradation, which is within our defined budget of 5%, which means that the improvements are additive. And we know that from this ablation study that each component can contribute positively, and the work can actually synergize and build up on top of each other. So now let's look at how our controller actually behaves in practice. And we have like this figure, which has 2 panels, and they complete the story of the adaptive resource management. For starting with the panel A, we show that for a 60-minute trace of our controller responding to dynamic interference. And as you see, we have this mean network time component, and also we have 2 y-axis for each of these panels. As for the left one, there is actually the interference level, and these are the red spikes that you see throughout the trace, and the spikes represent where our noisy neighbors, T2 and T3, become active, and they create PCI contention and compute pressure. And if you look at the color stack bars, these show which type of intervention the controller has selected at each moment. Orange lines represent lightweight guardrails, things like MPS quotas and IO throttles, and green bars are PCIe-Aware placement moves, migrating a tenant to a different MIG instance. And blue lines are the heavy intervention, which we do full MIG reconfiguration and changing the profile size. So if we look at the pattern of what's happening, the controller doesn't immediately jump to the strongest action. And during the first interference burst around minute 5, you see mostly orange. It tries to guardrail first. And as interference persists around the minute 15, we see more green. The placement moves. And only when interference is severe and sustained, around like minute 40, we see the blue MIG reconfigurations. So also for the panel B, we see the efficiency versus SLO compliance trade-off. It's really the heart of our evaluation. The x-axis shows resource utilization efficiency, and also so which basically means how much of the GPU pool we're actually using productively. And the y-axis shows SLO compliance rate, what percentage of requests meet their latency target. And if we look at the purple stars, that are our full system combining all the 3 components, at the cluster up in the top right, 90% SLO compliance at 70% resource efficiency. And the dashed gray line shows the efficiency frontier, best possible trade-off curve. And yeah, that's how it works. So for the next figure, we have this one, which is really drives home why PCI contention matters so much for tail latency. What we're looking here is a probability density plot, which essentially shows the distribution of latency values under different levels of PCI contention. The x-axis is inference latency in milliseconds, and the y-axis is the probability density. The area under each curve represents the probability of observing latencies in that range. And so for a green curve, this is the low contention, essentially an isolated tenant. The orange line represents medium contention, maybe the one noisy neighbor sharing the PCI path. The distribution actually broadens and the shift, and it's actually shifting right slightly. So if you notice the red curve, this is a critical one. And this represents static MIG under high contention from both T2 and T3. Look at what happens. The distribution becomes bimodal and with a very long and heavy tail. This is a small peak around 10 milliseconds. Those are lucky requests that happen to avoid contention, but there is a huge mass of probability extending all the way past 20 milliseconds. So what is causing this heavy tail? It's actually PCI bandwidth contention. When T2 is aggressively moving data between host and GPU, T3 is also active, and they are all competing for the same PCI root complex. So even though MIG provides compute isolation, they share the PCI path and they create a bottleneck. Data transfers get queued and inference requests sit waiting for model waits or intermediate activations to transfer. So this figure is important because it shows that the PCI topology awareness matters and software level isolation is not enough. You need hardware-aware placement to avoid these bottlenecks. Now, the real-world application, LLM serving with VLLM on almost 7 billion parameter instruct. This is a production-ready inference stack with the streaming output. We set an SLO of time to first token of P99 under 200 milliseconds. Under the same interference from T2 and T3, a static MIG gives us 232 millisecond TTFT for P99, and our full system reduces this to 199, just under our SLO threshold with only 4% throughput cost. And this 13% improvement in TTFT directly translates to better user experience for interactive applications. And crucially, we achieve this without any controller changes. It just works with the LLM workflow. And how do we compare to existing systems? This table shows both qualitative and quantitative comparisons. Qualitatively, our approach is unique in combining the dynamic MIG, PCI awareness, and VM deployability. Migrator pioneered dynamic MIG, but doesn't handle PCI topology or inference constraints. Miso explores cluster scale MIG, but required centralized orchestration, and a Sponge provides SLO over temporal multiplexing, and MPS offers flexible sharing, but weaker isolation. Quantitatively, under identical interference conditions, T2 and T3 active 40% of the time, Our system achieves the best SLO compliance, 11% miss rate versus 13 to 16% for others. MPS achieves a slightly higher throughput, but with worse tail latency. Our system strikes the best balance for latency-sensitive workloads. What about overhead? MIG reconfiguration takes about 18 seconds on average, which is why we limit frequency. The controller intervenes about 4 times per hour under dynamic interference, but uses less than 2% of CPU. The key limitations that this work has, and we need to acknowledge, is PCI topology may be partially opaque in some clouds, requiring inference from counters. MIG reconfiguration pauses tenants briefly, so bursty workloads may perceive disruptions. And our placement heuristic is simple, leaning-based predictors, which could improve stability. These are areas for future work. And so you see here an algorithm, which is the multi-tenant controller. So this is a schematic algorithm for how our model works. And here is the parameters of the controller regarding threshold, persistence, dwell time, cooldown, and other components. So for the conclusion, we presented an elastic resource allocation controller for multi-tenant LLM interference that combines dynamic MIG reconfiguration, PCIe-Aware placement, and lightweight guardrails. On a 16 GPU cluster serving VLLM workloads, we achieve 32 SLO miss rate reduction and 10 to 15% TTFT improvement with minimal throughput costs, making this suitable for serverless and elastic cloud platforms. Critically, the controller operates within VM boundaries using only host-level controls and no fabric privileges needed, making it widely deployable. Future work includes larger scale validation, learning-based placement policies, and extending to agentic application with more complex latency requirement. Thank you very much.
Okay, I think unfortunately we do not have the presenter joining, at least for now. So I believe we should just move on. If there are any questions, please put them into Discord channel, and presenters will be checking the channel for questions, and hopefully he can join in afternoon, but no guarantees on that. I think we should...
You'll be here in person, right? You're saying in the afternoon?
He's trying, but the best seems he was saying probably is to find some place he could connect from airport.
All right.
But yeah, that's the... So we have the last talk, which is Elena, which is remote talk.
Yes.
I can see you and I can hear you. Try to do screen sharing.
Vale.
It looks very good.
Yeah.
Sorry. Wait, because I'm trying to put the...
No hurry. Make sure it's all set up correctly.
So
everything looks good. It's full screen.
Vale, okay. Hi, everyone. Today I'll be presenting our work on serverless elasticity, specifically through our real Metabolomics use case, which is the Metaspace annotation pipeline. So before getting started, let me just say a few words about me and our group. This is me in the photo. I'm Elena. I'm an undergraduate student in Rovira i Virgili University in Tarragona, Spain. I am currently studying a double bachelor's degree in biotechnology and computer engineering. I'll finish up this year. And I'm also a research intern in the Cloud and Distributed Systems Lab, also at the university. This work is co-authored with Germán Izaguirre and Enrique Molina Jiménez, who are also researchers at Cloud Lab and my supervisors on this project. And regarding our group, it is led by Professor Pedro Garcia, and we work on serverless platforms and cloud computing, which is exactly the context of what I'm going to talk about next. These are the contents of the presentation. I'll first explain a bit of what the Metaspace platform is and how the metabolite annotation pipeline works at a high level, then motivate why this kind of workflow is challenging, describe our serverless design and the tools that we used, and finally show how this behaves in terms of scalability and elasticity, including some optimizations we did for the data ingestion stage. Okay, so before talking about serverless, I'll briefly introduce the domain that we are working with, which is spatial metabolomics. Metabolites are small molecules that take part in key processes in our bodies. By looking at these molecules, we can learn many things like how diseases develop, how drugs work, or how tissues respond to different conditions. In this field, we don't just ask ourselves which metabolites are present, but also where they are located inside a tissue. At the top row of the slide, you can see the typical experimental workflow in spatial metabolomics. On the left, we start with a tissue sample that is prepared and put on a slide. Then in the middle, an imaging mass spectrometer scans the tissue. It basically shoots the surface with a laser, and for every pixel on the tissue, it measures what we call a full mass spectrum. From those spectra, we can reconstruct molecular images. For a given metabolite, we look at its signal across all pixels, and we get a bidimensional map of its intensity in the tissue, telling us where it locates and under which concentrations. And this is extremely useful in biology and medicine, for example, to see how a drug distributes in a tumor. All these measurements are then stored in IMCML files, which are the raw imaging mass spectrum data that we want to process. During analysis, and this fact is really important, this raw input can expand internally by about 10 to 100 times because we generate many intermediate tables, centroids, and images. So now let's take a look at what this metabolite annotation pipeline actually is. At a high level, the annotation pipeline transforms the raw IMCML file into annotated ion images like the one you can see here. The two main inputs of the pipeline would be the dataset, which contains the spectra for every pixel in the tissue, and then the reference molecular database, which is a list of all the candidate metabolites and their theoretical spectra. Basically, the pipeline loads and partitions the dataset, prepares the molecular database, and then compares spectra against all the candidates. So we find where every metabolite is located inside the tissue. As I said before, this is not done in a single step. There are 15 stages in total, and each one of them, in this case, is implemented as a parallel cloud function that runs over some partition of the data. In table 1, we can see a classification of these stages that we did for this work. They can fall into 4 main categories. On the one hand, dataset dependent stages like upload partitions and merge segments. Both of them belong to data ingestion, by the way. Their cost and requirements grow with the size of the imaging dataset. On the other hand, database-dependent stages, which grow with the number of molecules in the reference database. Then stages that depend on both the dataset and the database, and finally, the static stages. These categories will be very important later for our experiments, and we also name them with different acronyms for the sake of clarity. So you may be wondering, why do we care so much about serverless in this workflow? And this pipeline, you see, is not a single monolithic job. It's a multi-stage DAG, like the one you can see on the left. Each box is a stage in the pipeline, and the arrows are data dependencies between the stages. Besides, each stage has its own computational requirements, so each one wants a very different level of parallelism and resources. Some stages are light and can run only in one function, while others naturally want hundreds of parallel workers. You can see this behavior in the plot on the right. This is a single run for one small dataset of only 50 megabytes that we did at first to try out the pipeline. The y-axis shows how many Lambda functions are active over time, and so we can see basically 4 big waves corresponding to different stages. So here you can see that even within one run of the same pipeline, these stages have very different parallelism needs. Now you'd understand that if we run this on a fixed cluster, we immediately have a slicing problem. How many cores, how much memory do we allocate so that every stage runs efficiently and independent from the input size? Because if we over-provision, we waste money. But if we under-provision, we may create bottlenecks. Besides, most researchers using the Metaspace platform nowadays are not cloud experts, not even computer scientists. This means that for them, concerning about manually configuring VM types, cluster size, auto-scaling rules, that becomes a huge problem too. This is why serverless is attractive in this use case. Cloud functions give us a pay-as-you-go execution and can scale from 0 to 1,000 of concurrent invocation when a stage needs it, and without the user having to worry about infrastructure. However, most serverless work in the literature still focuses on micro benchmarks or very simple workflows. So with this work, we wanted to look at a real production-grade pipeline and see in practice where serverless elasticity works well and also where it doesn't. So now we'll see how we actually run this pipeline in a serverless way. So we implemented this workflow using Lithops, which is a multi-cloud serverless framework for Python. With Lithops, we can write normal Python functions and the framework runs them as cloud functions in parallel. Specifically for our setup, Lithops uses AWS Lambda to execute all the stages and Simple Storage Service, S3, as the storage backend. So every stage you saw in the previous diagram is a Lambda function, reading and writing its data from S3. On top of that, we use Pyrun as the orchestration layer. Pyrun gives us a managed serverless Python environment. It builds the runtime once, launches the list of executions, and collects CPU, memory, and other interesting metrics for all the function invocations. Here you can see a few visuals on Pyrun. It is an active research and engineering project in our group. The idea is to abstract most of the operational complexity of cloud development and also pipeline execution. It also integrates multiple execution backends, and so the user can access them through the interface. So, as I said before, Pyrun acts as the orchestration layer. It builds runtimes, launches executions, gathers metrics, and this way it is much easier to experiment with large data pipelines like this one. Okay, so now with this slide, I'll try to explain the experimental setup that we used for the evaluation of the pipeline. We run two main experiments. In the first one, we vary the database size while keeping the dataset fixed. In the second one, we did the opposite. We vary the dataset size, keeping the reference database fixed. We basically want to see how the pipeline reacts when we play with these two inputs. In the tables, you can see the exact information about the experiments. And by the way, chunks and segments are configuration values, and they translate into a number of parallel functions for the upload partitions and merge segment stages, which are the ingestion stages. We use the same values for the first experiment because the database size does not influence on them, but the number increases in the second experiment as the dataset grows. So now let's see what happens when we increase the database size while keeping the dataset fixed. For the first experiment, we fixed the dataset to 1.8 gigabytes. And first of all, you may be thinking that, well, 1.8 gigabytes is rather small for nowadays data analysis. But the truth is that this size is greatly expanded through the pipeline stages. For example, in PCS, with the 12,000 formula database, the aggregate volume of processed data reaches about 100 gigabytes. This is because in this stage, we compare the dataset against all possible spectra found in the reference database, and the final result is huge. So in this plot, you can see in green the small database of 500 formulas, and in purple the largest one of 12,000. The y-axis shows the number of active Lambda functions at each moment, and the four indicated stages are the ones that change with database size. Basically, the four stages increase their parallelism, although the greatest change is in the GCC and PCS stages, from around 35 to more than 270 active functions. This means that for the database-dependent stages, the platform automatically scales from tens to hundreds of parallel functions, while the stage duration stays similar. So this is a very good example of serverless elasticity. When we increase the input size, we don't change any configuration, and the system reacts by adding parallelism rather than increasing latency. So this slide shows the same comparison of database sizes, but now looking at two simpler metrics. On the left, we have the total number of function calls per stage. The four database influence stages are highlighted in yellow, and you can see that the number of calls increases a lot when we move to the larger database. The system is clearly using more parallel functions to handle the extra work. On the right, we have the average execution time per stage. For those same four stages, their bars are very, very similar. Their workloads grow, but the stage latency stays constant. So this means that as the database becomes more complex and also the internal generated data increases, the platform reacts by increasing parallelism rather than increasing latency. And this is exactly the kind of elastic behavior we want from a serverless system. On the other hand, there are several static stages that also depend directly on the database size, the ones inside the red circle. And their execution time increases notably when the workload grows, which is what we'd expect. Besides, these two other plots are also interesting. Here I'm focusing on the same four stages that are mostly influenced by the database size and isolate their CPU and memory consumption to do these plots. On the left, you see the CPU usage per Lambda invocation. The average CPU stays low, around 10% for the small database and 8% for the largest one. On the right, you have the peak memory per invocation, where the average memory usage also decreases when we use the largest database. So even though the workload becomes much heavier and we launch many more Lambdas in parallel, each individual function is not getting close to saturating CPU or memory. This all shows us that the platform can keep a stable usage of resources. Okay, so far we've seen what happens when we grow the database, but now I want to show you what happens when we change the dataset size. So for the second experiment, we fixed the database to 12,000 formulas, and we run the pipeline on 3 different datasets, 1.8, 3.9, and 7 gigabytes. The plot shows again the number of active Lambda functions over time, but now for these executions. The stages marked in the legend are merge segments and upload partitions, which are our ingestion stages, and also save PNG chunks, which saves the images at the end of the workflow. This case is different because these 2 ingestion stages, although dataset dependent, do not scale their parallelism automatically. Their concurrency depends on the chunk and segment parameters we set. And in the red circle, you can see that as the dataset grows, we configure more chunks and segments, and so the number of active function increases. Also, in contrast to the database experiment, the end-to-end execution time is very different for the 3 dataset sizes. This is where the system struggles more, and it's one of the reasons why later we try to tune these ingestion parameters more systematically. So as we did with the first experiment, we also analyzed the total number of calls per stage, as well as their average execution time. Overall, you can see that for the dataset dependent stages, the total number of invocation rises with dataset sizes, which is what we'd expect. But this trend doesn't look the same for every one of them. First, look at the ingestion stages, which are indicated with the red arrow. As the dataset grows, and as commented before, both the number of calls and the average time of these stages increase. Even though we configure more chunks and segments and therefore get more parallelism, the ingestion time still grows with the dataset size. Then we have stages like GCC and PCS colored in orange. GCC is rather lightweighted, so what we see is mainly a big increase in the number of calls, although the time remains the lowest of all the stages. PCS, on the other hand, is more compute and I/O intensive, and here we see marked increases in the average execution time as well, which we attribute to more I/O traffic and data fetching latency. Finally, one of the static stages really stands out, which is GCB, highlighted in yellow. This is a static sequential stage that runs once to compute global segment bounds. Its average execution time increases drastically and becomes one of the main bottlenecks of the pipeline. So compared to the database scaling case, here we see that several stages do not keep their latency stable as we scale up the data. Finally, we also looked at CPU and memory usage for the ingestion stages. Regarding CPU usage, with the smallest dataset, the medium CPU is around 7%, but with the 7 gigabytes dataset, it grows to roughly 30%, with peaks close to 50%. Now on the right, we have the peak memory per invocation. The medium goes from about 160 up to 550 megabytes for the largest one. So unlike the database scaling case where resource usage stayed fairly stable, here both CPU and memory clearly increase with dataset size. That tells us that in this case, these stages are not scaling efficiently. They still work, but they start to push the limits of the runtime, and we would need further optimizations. So far we've seen how the pipeline behaves when we scale the database and the dataset size. The main pain point we found was during the data ingestion stages, especially for large datasets. And in the next question, I'll focus on this part of the pipeline and show how we try to optimize ingestion in a more systematic way. Okay, so in our pipeline, ingestion is basically a distributed sort of the IMCML file into partitions. It's implemented by 2 stages, upload partitions and merge segments, which we already mentioned several times before. The number of chunks we choose here is the same as the number of Lambda functions we launch. So performance depends a lot on this chunk size. Instead of hard-coding a value or tuning it by trial and error, we wanted a way to tune ingestion heuristically. That's where Data Plug and Data Cockpit come in. Data Plug is a tool that lets us partition scientific data directly from object storage. It understands formats like IMCML, which, by the way, you can just split however you want, and it uses more indexes and byte range reads to create partitions on the fly. On top of that, Data Cockpit is a widget built on top of Data Plug and integrated into Byron. It lets us explore datasets, pick one, sweep over different chunk sizes, and benchmark our functions, seeing execution time for each configuration. So the main idea is we isolate the upload partition stage, then we benchmark it on Data Cockpit, search for a good chunk size, and then use this configuration back in the pipeline. This is the methodology we use, which proceeds in 3 phases, as I said before. We first isolate the initial ingestion stage as a benchmarkable function. Second, using Data Cockpit, we partition each dataset with a range of chunk sizes from 30 to 130 megabytes, and we measure the stage's execution time for each configuration across the 3 dataset sizes. Finally, we cross-validate this by running the original stage with the same configuration parameters, comparing the benchmark times with the in-pipeline execution times. This way, we don't just tune ingestion in isolation, but also check that the chosen chunk size actually helps when the whole serverless pipeline is running. And now let's turn to the results. In the plots on the left, you can see the execution time of upload partitions with different configuration of chunk sizes, and each color represents one dataset size. For every point, we run 3 repetitions, and this is the average value. Figure 7a is the data cockpit benchmark, while figure 7b is the same experiment inside the original pipeline with the stage isolated. And well, the first thing to notice is that in both cases, a 50 megabytes chunk size is clearly the best. It gives the lowest execution time across all 3 datasets. Also, if you look at the curves, they basically have the same shape. They rise and fall in almost the same way. That is important because it means that Data Cockpit and our cockpit simulation function are really capturing the behavior of the real pipeline. So it is actually reliable for tuning parameters. On the right, you can see the bars for the speedups at 50 compared to 128 megabytes baseline, which is a common default chunk size in Cloud Analytics. We get around 1.72 speedup for the 1.8 gigabytes dataset, around 1.15 for the medium-sized dataset, and 1.13 for the largest one. Although the gains are clear when the chunk size is well chosen, the speedups decrease as the dataset get larger. So basically, tuning the data ingestion stage is beneficial, but its impact on the end-to-end performance of the entire pipeline is quite modest, actually. As input data grows, this stage becomes a smaller fraction of the total time of the workflow, while other stages, especially the sequential ones, become the main bottleneck. And finally, the conclusions. So to wrap up, here's the big picture of everything that we've seen. Our motivation comes from spatial metabolomics. These are extreme data workloads, and most Metaspace users are domain scientists, not cloud engineers. They just want to upload a dataset and get the IAM images back. But the pipeline behind Metaspace is very complex, with stages that need very different level of parallelism and resources. And those needs also change depending on the input size. If you run this on a fixed cluster, you immediately face all the usual questions. How many cores, how much memory, how big the cluster should be, and tuning all that manually is hard, especially for non-experts. So in this work, we run the whole pipeline fully serverless using methods on Pyram. This way, every stage becomes a cloud function, scaling up or down automatically. We saw strong elasticity when scaling the reference database. The heavy stages increased their concurrency while keeping latency stable. But with larger datasets, several sequential and IO-bound stages still dominate the runtime. And CPU and memory usage rise, showing clear limits. That's why we optimized data ingestion. Using Data Plug and Data Cockpit, we tuned the chunk size and found the best at 50 megabytes, giving up to 1.22 speedups for the ingestion stage. And for future work, the main opportunities would be reducing sequential bottlenecks, improving memory efficiency at scale, and exploring more parallelism in other stages. So thanks everyone for listening to this presentation, and special thanks to Germán and Pedro for guiding me and helping me out with everything. If you have any questions, I'll be happy to discuss them. I'm sorry if I'm being fast, Mary.
No problem. Are there any questions?
Okay, any question here? Seems okay here, Alec.
Okay, so I actually have 2 questions. One is, I think, simple, another maybe more. So the first one about cost, like if you make it very easy to run those pipelines for scientists, do you provide any way for them to keep track, how much money they are spending? Like I could imagine, they by mistake started thousands of pipelines running, and then at the end of the month they get a huge bill, and then they are surprised.
Actually, both I think in Pyram they are developing this tool, and in the pipeline you can see the cost. But are you asking me,
Yes,
how much does it cost?
And then maybe related, is the cost what they expect? Like before they run, do they know how much it's going to cost, or do they need to wait, sometime later to find out how much like storage was costing or
No,
serverless
I think,
functions and so
I
on?
mean, you can know the cost when the pipeline is finished, and it costs around. I mean, it depends on the data set, of course, but it costs around $1 to $5 more or less for
Okay.
each execution, which is good. And also in Pyrun, I think that they are trying to develop these. I mean, the thing to see the cost for every execution, for every workspace, and everything, and they are trying to put this. How do you say? That these metrics are shown to for the people that are using Pyrun.
Okay. And then the second was kind of related. You had it at the end that, the scientists, they may not be like actual developers. They may not know the technology. So what are your thoughts about like using AI or, some other way that they could describe the pipeline, like I don't know how complex it is to describe in English or Spanish or whatever, and then have it automatically create the updated logic of pipelines and then run it. Would it make it much easier for non-computer science users?
I'm not really sure, but I think that you have to know some basics about AWS Lambda. I mean, AWS and everything and all the platform in order to manually configure all this kind of thing, and also Docker and everything. And so it is quite difficult, and you cannot only rely on AI to do this by yourself. I mean, I think it's quite hard because it was for me, so I don't know.
Yeah, I understand. I think in our keynote there was a lot of AWS services and many options, right? Very hard to know
Yes,
which to use.
it's really easy to get lost once you have the entire console of AWS in front of you. So I think you must have some basics, and then you start develop, and you can rely more on AI. But at first you must know some. I mean, the basics.
Yeah, sounds good. Any other questions?
Yeah. Can you hear me?
Yes, go
Yeah,
ahead.
sure. As you said in the beginning of your presentation, you are indeed an undergraduate student. So how was for you your start with LitOps and your beginning with Pyren and LitOps and all this stack of software?
I don't know. It was messy. I'm not gonna lie, but I think I don't know. I mean, it was messy. I don't know what else to say, but yeah, I had to ask many questions, and I had to read a lot of documentation. And regarding the pipeline, it was, I mean, what was the hardest part of this was to understand the pipeline and the stages and everything.
Yeah, because the pipeline seems pretty
Yeah,
complex.
it's complex.
Like 15 stages, or
Hmm.
how many were there? Like 12,
And
a lot.
I mean, I'm supposed to have more information about the biology part and everything, but I don't understand. I mean, I understand them as a whole, but not every single one of the 15 stages.
Sure, that's interesting. Yeah. Nice to know.
Okay, thank you.
Thank you.
Okay, if there are no more questions, I mean, as I was saying before, you can always leave some questions